Welcome, periods, well, all the periods, 3, 4, and 6. Here we go. Periods 3 and 4 on Thursday in class we learned, we reviewed very quickly the 3D coordinate system, the dot product, and how to find the equation of a plane. And in period 6 you watched a video about this. So now let's kind of push on. There are 2 or 3 more things that you learned in this unit, and I think the way that Mr. Kirk does it, this is often like the last thing he does. So even when we have a normal year back at Blair, perhaps students are a little bit shaky on this because maybe there wasn't really any homework on it or tests on it or anything. But I guess last year probably even more so. People might have been a little bit checked out. So and if you totally learn this perfectly, then this will just be a little review. I want to talk about the cross product. Okay, what is the cross product of 2 vectors? Well, it is an operation that is really defined on 3-dimensional vectors only. If you take the cross product of 2 3-dimensional vectors, you get another 3-dimensional vector. And the idea is that it gives you a mutually perpendicular vector. Okay, so this definition has sort of 3 parts to it. One is that if you take the cross product, this is the notation, u cross v, of any vector, then it will be perpendicular to, or normal, people say when they're talking about vectors, it will be normal to or perpendicular to vector u and also to vector v. Okay, and so the picture is, I've never done this on a video. When I do this live, it's a little bit easier. Oh man. Let's see, the 3 most contrasting colors. So I have 3, man, I'm going to get really close to the screen here. I have 3 vectors here. I have no idea whether the depth perception is coming through. Hopefully it will. So I have 2 vectors here, this purple one and this green one. And the idea is that when I take the cross product of those 2 vectors, what I get is a mutually perpendicular vector. Okay, now, good. I think that's coming through. Okay, well, of course that's not enough of a description because there are an infinite number of vectors which are perpendicular. So you need to tell me something about the magnitude. And the magnitude, well, it goes like this. The magnitude of the cross product, remember the cross product of 2 3-dimensional vectors is itself a vector. The magnitude of that cross product is the magnitude of u times the magnitude of v times the sine of the angle between them. Okay, and there is some kind of justification for this definition, but okay, this is just the definition. Alright, and then if you are very astute, you will notice that this doesn't quite fully, that the Roman numerals 1 and 2 alone can't quite fully describe the cross product of 2 vectors because, oh man, I have to do this again. Because if I have this purple vector and this green vector, let me hold it like this, and I take their cross product, then there's always, even once you tell me what the magnitude is, there are always 2 vectors with a certain magnitude. There's kind of this one pointing up, and there's this one pointing down. Okay, and so we institute this thing called the right-hand rule, and the right-hand rule goes like this. You take your right hand and you put your right hand on the first vector. So if I'm going to do green cross purple, then I put my right hand here on the green vector and I cross it with the purple vector, so I curl in the direction of the second vector. and when I curl in that direction, my thumb points in the direction of the cross product. And so green cross purple in this case would be this vector here pointing up. But if on the other hand I did purple cross green, then my thumb is pointing down, so then the cross product would be coming down out of them there. Okay, that was not so great, but whatever. That is the definition. Okay, then there is just this long, that's good enough. Then there's just this sort of long derivation, which hopefully Kirk did this. I haven't taught this in many years. It takes 20 minutes or something. No, maybe not quite that long. But it turns out that you get this mysterious algorithm which enables you to compute the cross product. So okay, let's review this algorithm right now. Okay, I'm going to I'll just leave this up. So how do you do this? Well, okay. So I'm just going to do one example, and this is going to seem a little bit mindless because I'm not explaining why any of this is. I'm just going to do it, and hopefully you already learned why. And hopefully you did. Okay. So suppose I want to take the cross product of 3, 5, 7, and 11, 2, 13. Here's what you do. You make this box. Okay, this box is in fact called a determinant, and a determinant has something to do with matrices, and matrices are something we're going to learn in this class. So it's kind of chaotic for you to have done this last year, but anyway, there it is. And what you do is you sort of throw into row 1 of this determinant of the unit vectors I, j, and k. And then, as we've seen from this discussion I just tried to have, the cross product is, it's not commutative. It matters, u cross v is different from v cross u. In fact, they just point in the opposite direction. So it doesn't matter which one you put first. So the first vector, the one on the left, 3, 5, 7, you put that in row 2. And then 11, 2, 13, you put in row 3. Okay, and then you just do this thing, man, where you sort of move along this first row and you go like this. You go I, and then I guess this is what Kirk did. You sort of mentally imagine that the row 1 is deleted and the column 1 is deleted, leaving you with this little box, 5, 7, 2, 13. And then, for mysterious reasons, you subtract the j, don't ask why right now, and then you delete row 1 and column 2, and then you're left with the 4 numbers 3, 7, 11, 13. I don't know why I picked these numbers. And then plus k times, and then if you delete the row containing k and the column containing k, you get 3, 5, 11, 2. Okay, this is something called computing a determinant, and computing a determinant is something we're going to learn like in a week or two. And the idea is that if you already know how to compute a determinant, all educated people know this, then the formula for a cross product can be remembered by computing this determinant. Okay. Well, anyway, now what do I do with these weird little boxes? Well, then with these weird little boxes, I do sort of diagonal multiplication. So I do 5 times 13 minus 2 times 7. And 3 times 13 minus 11 times 7. And going from top left to bottom right, 3 times 2 minus 5 times 11. Okay, and so now just some sort of glorious arithmetic here. What do I get? 65 minus 14, 39 minus 77, 6 minus 55. So, what is this? 51 minus, and that's negative something, 38, I guess. And negative 49. Okay, and so what I end up with is the vector 51, 38, negative 49. And that is right, according to me, and that is the cross product of these two vectors. And since it's the cross product, I claim that it is perpendicular to each of them. And so if you want to check this, I'm not going to do this, but you can if you want. You can take 3, 5, 7, and you can dot it with 51, 38, negative 49, and you should get 0. Because the dot product of these two vectors is 0 because these two vectors are perpendicular. And it will also be true, of course, that if you dot the other one, 11, 2, 13, with 51, 38, negative 49, that you also get 0. Okay, and then the magnitude of this vector will be the product of the magnitudes of these two vectors times the sine of the angle between them. All right, so let's just suppose that you remember that now. Good. One more, well, I guess two more sort of new things. One thing that's actually kind of easy maybe to do is the equation of a line in 3 dimensions. So this is sometimes called the vector equation of a line. All right, vector equation of a line, but now the line is just sort of living somewhere in 3D. So I have a line, let's see, don't have a meter stick, but I have maybe like a this thing. It's pretty long. So the idea is that you have, some line, but the line is sort of pointing in some 3-dimensional direction. And I would like to come up with a way of talking about that line algebraically. Okay, well, I think this is actually very sort of straightforward. Let me draw a generic sort of line, and here's my example. Actually, I'll take sort of one step back. I'll phrase this a little bit more normally or something like that. I'll just say find the line through, and then I'll give 2 points. P, let's point P be 1, 2, 3, and let's point Q be 7, negative 2, 6. Okay, so this seems like something we should be able to do. If you give me 2 points in 3D, then there's only one line that connects those 2 points. So what is the equation of that line? All right, well, let me draw those points here. So let this be point P, and let this be point Q. One second. So that's 1, 2, 3. It's point P, and point Q is 7, negative 2, 6. Okay, I'm not trying to make this picture accurate, but you kind of get the idea. All right, and now the next sort of step is the only one that involves any real thinking, which is how do I find the equation of a line, just in general? How does one come up with the equation of a line? And the answer is, once again, as we talked about before, you pick an arbitrary point on that line, and you tell me what's true about that arbitrary point. So I'll pick some point, and I'll call that point, say, R, and I'll let the coordinates of R be x, y, z, and the only thing I know about that point R is that it's on that line. And if you can tell me what's true about the point R, then you've told me what's true about every point on that line, and then you've described all the points on that line, and that's just the equation of the line. Okay, so what is true about that point R? Well, this one I think is pretty easy. That point R is kind of like goes along sort of through the vector connecting P and Q, or something like that. So if you have this vector connecting P and Q, I'll sort of go over this now in black. then you should be able to get to point R by like following this along from P. And so now the idea is, let me take the origin, O, which has coordinates 0, 0, 0, and I'll say, okay, well, I can think of two different ways to get to this vector R. One way to get to the vector R is to just go straight there from O to R. And yet the other way to get to vector R is to first go from O to P and then to ride the PQ train some number of times. And in this case, it looks to be, roughly speaking, about 2 times. Okay, and so there it is, right? This vector, OR, is really just the vector OP plus some number of PQs. And I use T as just representing a so-called parameter. It's just some real number. So there you go. You go from O to P, and then you do the PQ some number of times, not necessarily an integer. Okay, and that's it. So what is the vector OR? It's x, y, z. What is the vector OP? Well, it's the vector from O to P, so it's just the vector 1, 2, 3. And then I multiply sort of T by the vector PQ, and the vector PQ, well, from P to Q is, the displacement vector is 6, -4, and 3. Okay, good. And now I call this the equation of the line. And it's the equation of the line in the sense that for any single real number t that you give me, when I compute the right-hand side, it's a point on this line. And for any point on this line, there is a real number t which will direct me to that point. Okay, that's everything basically you need to know from that whole unit, I guess. How to find the magnitudes of two vectors, how to find the dot product of two vectors, how to find the angle between two vectors, how to find the equation of a plane, how to do the cross product, and how to come up with the vector equation of a line. And then there are just some sort of like tasks which you maybe did last year, maybe not. For example, one sort of a classic kind of task is, given 3 points, find the equation of the plane through those 3 points. And I'll just mention sort of very briefly how to do that. So here is my 3D coordinate system. Suppose I give you some kind of plane, and then I give you 3 points, A, B, and C. And I give you the coordinates of those 3 points. Well, it's just true geometrically that 3 points, 3 non-collinear points determine a plane. So you should be able to come up with a plane with just this information. How do you do it? Hopefully you did this last year. The move is you construct vector BA and vector BC. Doesn't matter which way you do it. And both of those two vectors now lie in that plane, and then you take the cross product of them, right? So you get B cross BC, say. And well, when you take the cross product of those two vectors, what you get is a normal vector, and that normal vector will be perpendicular to each of those two vectors. And since it's perpendicular to each of those two, it's perpendicular to the plane, and thus you know the normal vector of a plane, and now you can finish the problem. And there are many other kinds of little tasks such as this. But I thought there's one that we could do right now because it's sort of interesting, and then this will be the last thing that we do in this video. Okay, and this task is to find the line of intersection intersection of two planes. Okay, if you give me two planes, then there are only two possibilities. They're either parallel to each other or they intersect. If they intersect, then their intersection is a line. So I want to know the equation of that line. So this maybe sounds kind of hard. I think it is kind of hard. And it's this sort of thing that's really helpful to do live. But anyway, x minus y minus 2z is -1, and x minus 3 y minus 3z equals -7. Once again, I've picked more or less arbitrarily some planes. I'm sorry for this mark. I'm going to get new boards, I think, at some point. Okay, so let this be plane P, let this be plane Q. Now, if you look at the normal vector to this plane, the normal vector to this plane is just formed by taking these coefficients. So the normal vector here is 1, -1, -2. And the normal vector here is 1, -3, -3. And those are just not scalar multiples of each other. And therefore, these two planes have different normals, which means these two planes are not parallel. And so, in fact, these two planes will intersect. Their intersection will be a line, and I want to find the equation of this line. All right, back at Blair, I have a whole white pair of whiteboards that I duct taped together 10 years ago or something. But right now, this is the best I got. I have I have this red folder. So think of these two sides of the folder as being the two planes, and then the seam where they meet, which I have highlighted with this kind of blue ruler, is the line where they meet. Of course, this line is. Oh man! All right, look at this. So this, yeah. This line is infinite, and it's the line of intersection of the two planes. Okay, how are we going to do this? Well, normally back at Blair, I give everybody like 10 minutes in groups to kind of work on this problem, and I would say usually people don't figure it out. Although in some years, the previous Precalc B teacher did a lot of these kind of problems, depending on whether they ran out of time or not. So if you've done this before, then maybe you remember how to do it. But I bet you didn't. I bet you didn't do this last year. So let's just do it now. Okay, and it's very interesting and very sort of non-obvious, I think, what to do. And okay, here we go. I want the equation of this line, and notice that we reviewed how to find the equation of a line. It's sufficient to know the direction that the line points in and one point which is on the line. Okay, well let's first talk about the direction the line points in. So I have this blue ruler. How can I know, given the equations of these two planes, how can I know what direction this line points in? All right, here we go. Let's see if this works. I bet this is not going to work. Okay. How am I going to do this? I'm trying, guys. Take normal vectors to the two planes. And let this blue vector be, oh my gosh, oh man. Even live in class, I usually have someone help me with this. So let this blue vector be perpendicular to the plane that it is coming out of. There it is. And let this red vector be perpendicular to the plane that it is coming out of. Okay. Well, now these two sort of meet. These two vectors. Well, it's not that they meet. It's that these two vectors now kind of point sort of directly out of these two planes. If you now take the cross product of these two vectors, this is the part that's going to be kind of impossible, but if you take the cross product of these, I don't know how I'm going to do this. Oh man. Well, this is just a failure. But I'm trying here. If you take the cross product of these two vectors, then it is a new vector which points in the direction which is perpendicular to both of them. But if a vector is perpendicular to both of these planes, both of these normal vectors that are sticking out of these planes, that vector is in fact parallel to the direction vector of the line. Okay, I don't know whether that worked. I can also draw it, but well, okay. We'll just hope that that worked. So in other words, if I take the normal vector to this plane, which is the vector 1, -1, -2, and I take the normal vector to this plane, which is 1, -3, -3, then those two vectors coming out of those two planes, I'm just going to have to show you a picture later if you don't get it, or try this at home on your own. Those two vectors, if you take their cross product, it's actually not that hard, then it's parallel to the line of intersection. Okay, and so I'm just going to do that right now, and I get, I now take the cross product, so I want to do 1, -1, -2, cross 1, -3, -3. And IJK, 1, -1, -2, 1, -3, -3. And this can be computed via that kind of mindless algorithm that you learned last year, which I just reviewed. So okay, you get I times minus, for obscure reasons, J times plus K times, yeah. And so this is 3, a lot of negatives now, so it's getting confusing, minus 6 minus J times -3 plus 2, because it's minus -2, and this is -3 plus 1. So I think I get -3, 1, -2. Yeah, I think that is right. And this vector now is the direction that the line of intersection points in. Okay, and so now here's kind of where I am. The overall goal was to find the vector equation of the line. So that can be written as x, y, z equals some point on the line plus t times -3, 1, -2. Okay, and so good. Now all I have to do is just find one point on this line, and there's not just one answer, there are an infinite number of answers. I just need to find one of them. Okay, so that is now a sort of a separate problem. How do I find a point which is both on plane P and also on plane Q? Okay, and there's not just one way to do this, but here's a way, and the way goes something like this. If I have my two planes, then probably those two planes are not going to be parallel to the ground. So the ground is the xy plane. The ground is the place where the z coordinate is 0. And so if the z coordinate is 0 everywhere on the ground, then here's what I want to do. I'm going to consider the first plane, this one over here with this kind of white label on it. This plane is going to hit the ground somewhere. Wherever this plane hits the ground, that's going to be a line. So that's going to be all the points that are on this plane, but also on the ground. Well, if the if it's on the ground, then the z coordinate must be 0. And there's just a way to do that, right? Because what is plane P? It's the infinite number of points such that x minus y minus 2z is negative 1. But if I add the condition that the z coordinate is 0, well, then I just get x minus y equals negative 1. And so what did I do? I just set z equal to 0. But instead of setting z equal to 0 mindlessly, I set z equal to 0 with the understanding that what I end up with is a line, and this line is, this equation is the equation of the line where this plane meets the ground, the xy plane. And now I just do it again. I take the other plane, this other one here, the one that doesn't have the white label on it, and I also let it hit the ground. The ground, also known as the xy plane, is the place where the z coordinate is 0. And so if I just set z equal to 0 here, I get x minus 3y equals negative 7. And, well, what is this? This is the place where the plane hits the ground. So now I have these two lines on the ground. Well, wherever those two lines intersect is a point which is on both of those lines, and hence, since those lines are each on these two planes, is a point on both planes. Okay, so what I now need to do is to solve this system of equations to figure out where these two lines meet. And, well, maybe the simplest thing to do is to just subtract the two equations. Let's do this kind of old style. And if we do that, we get 2y equals 6, so y is 3. And if y is 3, then x is 2. Let me just double check that. Yeah. Therefore, the point 2, comma 3 is the point on the ground where these two lines meet. And so really, it's the three-dimensional point 2, comma 3, comma 0, which is on both of these planes. So this point is on P, and it's on Q. And you can just double check that that's true. It's the point which is on P and also on Q and also happens to have a z coordinate equal to 0. If you've been following this, there was nothing special about the plane z equals 0. We could just as well have easily set z equal to 1, say, and that would have given us a point something something comma 1, which would be the point where these two planes would well, never mind. It works perfectly well too. But okay, now we get to fill in the question mark, which is that 2, 3, 0 is a point on both of those planes, and so the equation of the line of intersection of those two planes is go to the point 2, 3, 0 and follow an arbitrary number of times this vector, which is the vector that we found to be pointing in the direction of that line of intersection. Okay, I think that's pretty hard. It actually requires you to have a good understanding of equations of planes, of normal vectors, of the cross product, of systems of equations, of the vector equation of a line. So in some ways this is kind of maybe the culminating activity or something of this unit. So good. You are now going to do some homework problems from our textbook. I'm aware that like half of you have the textbook still. For the ones who responsibly turned it back in, you are hopefully getting that book back again, maybe next week or something. But I guess I'm going to scan in all the pages, or I'm going to retype them. Chapter 11 is the chapter from our textbook about all of this stuff. Based on the way Mr. Kirk teaches, I know he barely used the textbook, and I don't think he even ever really said, like, read the book or anything. I like textbooks. I trust you guys enough to be mature enough to be able to read a textbook. Maybe not all of you, but maybe some of you like learning math from someone other than me or other than a person. So if you're feeling a little bit shaky on all of these things because you forgot, because it was a long summer, because you checked out with the last 2 weeks of school last year, because you already got your pass and you were like, I'm done, then a good thing to do would be to just totally reread chapter 11 in this textbook. And hopefully there's nothing new in that chapter. Everything in that chapter I just reviewed over these past little videos. But you might learn something new, or maybe the pictures are nice. For those of you who handed in your textbook, I will try to scan in all of chapter 11, maybe, so that you can read it. And we'll have some homework problems over this weekend, which has already begun, to review some of these problems. And the homework is a little bit hard, so we will maybe go over it somehow. Okay, thanks and bye.